Welcome everyone. Today I'm going to explain or present the course project that is design and implementation of a custom 8-bit microprocessor on FPGA. This is the course project and done by our semester project group and which is submitted to Professor Ramkazi. Professor Dr. Ramkazi Burath. Again, the introduction. It is a 8-bit processor designed entirely from VHDL, and it has it is a 8-bit microprocessor which in which 4-bit is opcode and 4-bit is address, with 6 instruction set, that is move, add, subtract, or store and NOP operation, and there are 3 registers. And all the components are implemented in VHDL. The instructions, the components are PC, which stores the address of the next instruction memory, and control decoder, register file, ALU, data memory, and it uses the 2-cycle store operation to write in the memory, and all the components is verified in a VHDL test bench and 7-segment display, and demonstrated the 2 distinct test programs on real FPGA hardware. And this is the overall architecture of the microprocessor, and there is a program counter which holds the memory address of the next instruction, and instruction memory, that is the place where the instructions were stored. And control decoder, it will generate the signal that which operation will be done, and register file in which register the operation is being done, and ALU operation operates add, subtract, or and all operation is done in the ALU, and MUX will the control decoder will give the signal to the MUX whether to select from the data from the ALU or from the direct memory. And data memory is used to store the memory data in the memory, and to store the data in the memory we use the 2-cycle operation. So store FSM is the main building block for this microprocessor. These are the opcodes and memory addresses. Memory addresses, there is a 16 slots of memory, and there is opcode, 6 opcode. Upper nibble of the code is opcode, and lower nibble is 4-bit memory address. We can select one of 16 data memory locations. Clock strategy and timing. We have used 24 megahertz frequency microprocessor, and which will lead to go for 40 ns clock cycle. These are the opcode. Move A, add A, it will do the it will memory address. There is a instruction clearly written here, so I will explain this instruction there. So 2-cycle store instruction, I already told that. And component design, this is the design for MUX that whether to select from the ALU operation or from the direct memory. And test program, this is the test program. From this we can learn how the instructions work here. And memory 0, let's say in memory 0 there is a 5, and move A to memory 0 means A store the value of the memory 0, that is 5, and B gets the memory 1, that is if memory 1 holds the memory value 3, then B will get 3. Add A memory 1 means A has 5 and B has memory 1 has memory 1 has 3, so 5 plus 3 is 8. Likewise this operation goes here. Add A, move move C memory 2 means C gets the value of memory 2, and memory 2 has the 0A value, so it is stored here. Likewise store cycle 1 address 5, and store cycle 2 data This address, in address 5, there is a data 0 into 33 stored by this instruction, and move a memory 5. Memory 5 has 33 data, so it is stored in the A, and no means it will freeze the operations. Likewise, simulated in the VHDL. And likewise, this instruction also works similarly. No need to explain twice. I think so. And this is the target is this we have done in this FPGA board, and it has 100 MHz oscillator, 8-digit multiplex 7-channel display, and design hierarchy. This is the design hierarchy, how we done that, and we have selected 25 megahertz 14 ns clock period. This is the synthesis and implementation result. The on-chip memory power in 0.063 watt, and junction temperature is 25.3 degrees Celsius, and on-chip power 64 milliwatt. And in this operation, we are expecting the 33 and observed the 33. In this operation, we can see there is a 33030A, and we have got the 33030A, 33030A, 33030A. That is the FPGA board. We can see the output, and for the another output 004FB3, 004FB3, we have got the output in the hardware too. And there is a challenge of 8-bit storing 8-bit data. 8-bit the operation stored has the 16-bit memory operation, so we cannot do it in one cycle. Other operation is done in one cycle, so it is divided into 2 cycles. And reset is not happening in the FPGA board, so we process variable with explicit reset each activation, and timing violation at 100 MHz because we have done all the fetching, decoding, and executing in one cycle, so it needs some more seconds to complete that, so we use 25 megahertz, and digit 3 showing an E on display, so we reverse the connection which is in the FPGA board, and it shows the correct value. Conclusion: successfully designed and simulated this 8-bit processor on FPGA hardware, and all the design functionality of the opcodes like move, add, swap, or store across the 3 registers, and we have done 7-channel display is done. And okay, I already explained all other things. VHDL timing schematics, synthesizable versus simulation only constructs, FPGA timing analysis, and hardware debugging. We all learned that. So we built a 8-bit microprocessor with 6 opcodes and 3 registers, and we have implemented the store operation. There is a 2 cycles, and this is the course project for our digital circuits and system design for the 6th semester of electrical and electronics engineering, specialized in power and control, which is taught by the Professor Dr. Ramkaji Brathwagi. And this project values 15 marks for our internal, so good luck for us. Thank you.